camera action. Right, so these last two problems of the course will deal with the Nerst equation. So let's do these two problems and finish off the class. Use the Nerst equation to predict the spontaneity of the redox reaction, shown below. So first thing is the Nerst equation. We're talking about non-standard state. Okay, we're talking about non-standard state. We're talking about E, some voltage, cathode and anode, V, voltage. Okay, not this. Not this, because that little symbol not means standard state. Okay, so we're calculating this. That is when we will use the Nerst equation. So spontaneity of the redox reaction. Redox reaction means somebody gets oxidized and somebody gets reduced. Okay, somebody gets oxidized, somebody gets reduced. They are a pair, or they are a couple. All right, so let's go ahead and do this. We have, let me also write you the Nerst equation. You don't have to memorize this. I'll give you this on the test. The Nerst equation is that's the Nerst equation, so I'll give you that. You do not have to memorize it. Okay, we're going to use this equation to solve this problem. Okay, non-standard state. One is at 1.94 moles over liter. The other one is at 0.15 moles over liter. All right, so in blue, let's have the CO cobalt go to CO plus 2. That's cobalt. Go to CO plus 2 aqueous. Okay, how many electrons and where do we need to put them to balance this? Okay, this is going to be 2 electrons on the product side. To get this balanced completely. So plus 2 and minus 2 makes it 0. So let's check out our sheet here. And what is cobalt? Where is cobalt? It's not here. Oh, here it is. Okay. Worried that these aren't here. Okay, so here's our cobalt. And looking at that, I'm getting minus 0.28 volts. Okay, a negative 0.28 voltage. Okay, so this is oxidation because we lose 2 electrons. So this is oxidation. Okay, and can someone tell me where does oxidation happen in a battery? Does it happen in the anode or cathode? All right, it's going to happen in the anode. Okay, and ox. And then we'll flip this, okay, because this is the flip of that. When we flip it, that will be positive 0.28 voltage. Okay, remember these numbers do not change, so it's going to be positive 0.28 volts. All right, everyone good with that? All right, now in the pink, let's do iron plus 2 going to iron solid. How many electrons on and where do we put them? Okay, we're going to put, everyone see this, 2 electrons on the reactant side to balance that. Is everyone good with that? And Fe plus 2 plus 2E minus goes to Fe solid. Where is that here? Okay, it's right here. That's negative 0.44 volts. And this would be, is this the anode or the cathode? Okay, is this oxidation or reduction? Okay, so this is reduction. We gain 2 electrons. Reduction occurs at the cathode, red cat, reduction cathode. So we'll do E cathode, and that number is minus 0.44 volts. Okay, so we do not need to multiply anything because the 2E cancels. How many electrons are being reduced in this reaction, or how many electrons are being transferred in this reaction? Okay, this is a 2 electron transfer reaction. This is a 2 electron transfer reaction. And so we're going to get CO solid plus Fe plus 2 goes to Fe solid plus CO plus 2 aqueous. And we add these two guys up, and what will we get? 0.28 minus 0.44. It's going to be 6.16, negative 0.16 volts. Is that right? Yeah, negative 0.16 volts. All right, so this is going to be E cell. Okay. E cell, which is the battery cell, cathode and anode, we put them together. All right, and now we'll use the Nerst equation. And we'll solve for this. E equals E naught minus 0.0257 N natural log Q. Okay, let's figure out Q now. Q is going to be products over reactants. Q will be products over reactants, no solids. So it's going to be CO plus 2 concentration divided by Fe plus 2 concentration. All right, cobalt plus 2, what do we have here? We have 0.15 big M moles over liter. Fe plus 2, we have 1.94 moles over liter. So what's 0.15 divided by 1.94? How about 0.0773? I'll put some extra digits here. Bless you. That is Q. Bless you. Okay, that is Q. All right, so E is going to equal to E cell, which is minus 0.16 volts, minus 0.0257 divided by 2. Remember, this is a 2 electron transfer reaction, times natural log of 0.07732. Let's do this on our calculator. Natural log of 0.07732 times a minus, okay, that sign before it is a minus, times a negative 0.0257, close those parentheses, remember it's a times a negative, divided by 2, plus a minus, okay, look at the sign in front, minus 0.16, I'm getting minus 0.13 volts, and this should be our answer, okay, under these conditions of 1.94 big M and 0.15 big M molar. So this is how you'll do this problem. Nerst equation. and this is non-spontaneous. Okay, why is it non-spontaneous? Or favors the reactants? It's the same thing. Okay, the reason why is because of the minus sign. It's a dead battery. Okay, it's a battery that's not going to work. Now, if you flip this reaction, you get positive 0.16 volts. That's a battery, but you can't get a battery from this. So it favors the reactants, does not favor products, negative 0.13 volts, and that is the spontaneity. Okay, it's not a battery. Okay, so now we'll do the very last problem for this class, and that is page 14. Okay. Any questions? Let me know when you're ready to go. Everyone's excited. Nodding your head. You'll be excited when the problem is over. Probably you'll be excited when the class is over. Not the lecture material. Okay. Yes? All right, another Nerst equation problem, and then I'll end it. So, okay, we're using this type of notation. So make sure, please, I ask each and every one of you to know this. Okay, this is called the anode couple. Okay, those two lines there mean salt bridge. Salt bridge. And this is cathode couple. Okay, what happens at the anode? Oxidation happens at the anode. Okay, what happens at the cathode? Okay, reduction happens at the cathode. Okay, this thing once again is called salt bridge. It's just two vertical lines. All right, anode is the site of oxidation. So here we have Al solid. I'll put it in green. Goes to Al plus 3, aqueous. Okay, how many electrons and where do we need to put this? Okay, we're going to put 3 electrons on the product side. Right? 3 electrons on the product side to balance this. Plus 3 minus 3 is 0. And what is the voltage with that? This is oxidation, okay? Oxidation occurs at the anode. You're losing 3 electrons. Where is aluminum? There you go, towards the bottom. And this is oxidation. Let's flip this. Negative 1.66 volts becomes positive 1.66 volts because we flipped it here in the problem. All right, and then in the brown, let's do Al plus 3. No, in the brown, let's do copper. Going to copper solid. Anode, salt bridge, cathode. So we have Cu plus 2. Goes to Cu solid. How many electrons and where should we put this? Okay, let's put 2 electrons on the reactant side. Okay, so here we gain 2 electrons. Here we're losing 3 electrons. Here we're gaining 3 electrons. And this is reduction. Reduction occurs at the cathode. And then copper. Where is copper here? Copper solid. Here we go, right here. And that's positive 0.34 volts. Positive 0.34 volts. Right, so we will cancel out electrons. How many electrons are transferred here? Okay, I need to cancel out my electrons first, right? Okay, so let me cancel that out. To do that, I'm going to multiply the top one by 2 and the bottom one by what number? 3. Okay, so how many electrons are being transferred in this reaction? Okay, this is a 6 electron transfer reaction. Everyone see this? Okay, multiplying the top by 2, multiplying the bottom by 3 to cancel out the electrons. This is a 6 electron transfer reaction. This is a 6 electron transfer reaction. Okay, I got to get all my electrons out, canceled out. So 6 canceled. And we are left with 2Al solid plus 3U copper, Cu plus 2 aqueous. And that's going to go to 2Al plus 3 aqueous plus 3 Cu solid. And this is going to be 2 volts, exactly 2 volts. Okay. Considering most of the batteries are 1.5 or volts, this looks like a really good battery. Okay, and this is going to be E cell, okay, which is cathode and anode together. All right, so now this is standard state, but we are not at standard state. The last set of this problem is okay, the aluminum plus 3 is 0.15 big am. The copper plus 2 is 0.025 big am. So, okay, we'll plug this into the Nerst equation to get E cell, not at standard state, but at these concentrations, that state. So once again, our Nerst equation is this. E is equal to E naught minus 0.0257 n natural log of Q. So let's calculate Q. Okay, everyone, let's calculate Q. Q is going to equal to products over reactants. Okay, it's going to be Al3 squared divided by Cu plus 2 cubed. Okay, no solids, no liquids. Okay, the square because there's a 2 coefficient, and the cube because there's a 3 coefficient. Okay, so Al plus 3 squared is 0.15 squared. And Cu plus 2 is 0.025. We're going to cube that, 0.025 cubed. So 0.15 squared divided by 0.025 cubed. What are we going to get? Squared divided by 0.025 cubed, close the parentheses, 1440. Okay, so Q is 1440. Okay, remember, no liquids, no solids in that Q thing. Okay, 1440. So that is Q, products over reactants. Products over reactants. And now we will solve for this. E naught is 2 volts. Okay, this is our E naught. It's 2 volts. minus 0.0257 N. This is a 6-electron transfer reaction. So N is equal to 6. Okay, this is a 6-electron transfer reaction. N is equal to 6. Natural log of Q, products over reactants. Okay, don't forget the square for the 2, the cube for the 3 coefficient, and that is 1440. All right, natural log of 1440. Times a minus, okay, times a minus 0.0257 divided by 6 plus a positive 2. Plus, look at the sign in front, it's positive. So plus a positive 2, again 1.97 volts. And that looks to be my answer, 1.97 volts. So under these conditions, it's positive 1.97 volts, and this is spontaneous. Okay, it favors the products. Okay, the opposite before, the opposite from the previous problem, but this problem is spontaneous, and this problem it favors the products. Okay, 1.97 volts. So Nerst equation, non-standard state. You can expect a couple of those problems on this exam that's coming up. All right, well, everyone, so that is the class. So thank you for your perseverance. Okay, it's not easy. I'm sure it was very grueling for you, and not over yet. Okay, we have an exam. We made it next Tuesday. Your quiz is next Tuesday. Okay, turn in whatever you need to turn in on your Canvas. And on Monday we will review. All right, so once again, for those of you that came in a little late, I want to wish each and every one of you a very happy Thanksgiving. Okay, I'll see you here all on Monday for the review.